Okay, so we're now interested in finding the length of the arc along an arbitrary curve. So let's consider a continuous function. Say y equal f of x. And let's say it's just minding its own functionally business. And we come along and we decide that we have an x value here of a and another x value here of b. And what we're interested in is the exact length of this curve between a and b. So in other words, if we took a string and very carefully laid it along the curve, and then we just pulled the ends of the string, so the string was taut in a straight line, what would be the length of that straight line? That's what we're interested in. So this is called an arc length. We can call that length L. All right, well, how might you do this without calculus? I mean, suppose you had like a winding trail in the woods that you're trying to find the length of. Well, you could take the straight line measurement between 2 points along the curve using a tape measure, and then move to the second point and take another straight line measurement, and move to the next point and take another straight line measurement, and so on, and then just keep adding up these straight line measurements until you've got an approximation of the actual arc length of the curve. And you can imagine that the more points you sample, the more accurate your approximation is going to be. This, of course, makes it a natural calculus problem to kind of take the limit and get the precise length of the curve. So what we're doing is we're adding up these sort of segments here, and the question is, well, what's the formula for one of those segments? And then to add up all of them, we'll just throw an integral in front of that formula. So let's pick on this segment here and say, what's the length of this guy? Well, what we can do is figure out the length of that guy in terms of units that we're already able to deal with. For instance, this horizontal length we can call dx. It's a tiny bit of the x direction. And this vertical length we can call dy, which is a tiny bit of the y direction. So we can therefore calculate that this hypotenuse of the right triangle formed by dx and dy by the Pythagorean theorem would have a length of dx squared plus dy squared. And one could therefore conclude that the arc length L is merely the sum of dx squared plus dy squared under a radical. Okay, well, that looks certainly odd and unusual for an integral as we're used to seeing them. We're used to having an integral look like stuff involving x with a dx on the far right. Okay, well, let's play with this to make it look more like that. So we could see that this guy here is the integral from a to b. Well, let's factor dx squared, which of course means it will actually emerge as a dx. That leaves us with dx squared over dx squared, which is 1, plus dy squared over dx squared. Okay, well, this is actually perfect because we can move this dx factor to the far right, which is where we want it, and that leaves us with this radical of 1 plus dy squared over dx squared. Why don't we just consider that the square of dy dx? Dy dx being just the derivative of our function y. And then here's our dx factor, which is just moved over to the far right now where we like it. This is, in fact, the arc length formula. Let's notice a few things before we actually write a summary here. One, this formula requires the function that we're dealing with to be differentiable, since there's a derivative in the middle of it here. So at no point did we specify that our function was differentiable. In fact, all we said was that it was continuous, so we're going to have to strengthen that condition to be differentiable. 2, the derivative itself has to be continuous in order for the antiderivative of this integrand to exist. So that's 2 conditions. 1 is the original function has to be differentiable, and 2, that derivative itself has to be continuous. Well, the good news is pretty much every function we really deal with satisfies those conditions. All right, let's properly write down the formula. If f is differentiable and f prime is continuous on the interval a to b, then the length of the curve y equals f of x over the interval x extending from a to b is simply given by this formula. Integral from a to b, square root of 1 plus dy dx squared dx. Alternatively, you can use f of x notation, in which case we would say it's the square here of the derivative. All right, and while we're at it, we don't necessarily have to have y as a function of x. We could have x as a function of y. So in the analogous case, where x is equal to a function g of y, and we're ranging over c to d on y values, the arc length is the integral from c to d of radical 1 plus the derivative of x with respect to y squared dy, or in function notation, integral from c to d of giant square root of 1 plus the square of g prime of y dy. All right, so let's see some examples where we want to find some arc lengths. All right, so here we have a curve, y equal ln of cosine of x, and particular bounds. And we want to find the length of the curve between those 2 bounds. So, okay, yeah, I needed this calculation just the other day, buying tomatoes at Ralph's. So this is pretty relevant. So let's use the arc length formula. So clearly this is a function of x, and our bounds are x values, so we're integrating with respect to x, which means that it's the derivative of y with respect to x that gets squared inside the integral here. Okay, so it's pretty evident that a and b are probably 0 and pi over 3, but what we do need is the derivative dy dx. Okay, so dy dx is the derivative of ln of cosine. So derivative of ln of stuff is 1 over the stuff. And then by the chain rule, derivative of the stuff. So derivative of cosine is negative sine of x. So this comes out to negative tangent of x. All right, so therefore our length is the integral from 0 to pi over 3 of the square root of 1 plus dy dx, which is negative tangent of x, and that quantity is being squared, dx. So this is our setup, and from this moment forward, it's now just work out the integral mechanically, right? So hopefully something happens that's nice. Here the negative is insignificant because it gets squared, so we have radical of 1 plus tangent squared. Well, 1 plus tangent squared is secant squared of x. And we can reduce this to simply secant of x dx. And why is that? Because the interval that we're considering here is in quadrant 1, and secant values are all positive in quadrant 1. So we don't need the absolute value. Okay, so we now will find the antiderivative of secant, which is an automatic one. We know this one for free, so we'll just write it. This is ln of secant of x plus tangent of x, and our bounds are 0 to pi over 3. All right, so plugging in the bounds of the integral, we're going to get ln of absolute value of secant of pi over 3 plus tangent of pi over 3. And this is minus ln of absolute value of plug 0 in, so secant of 0 plus tangent of 0. So secant of pi over 3 is the reciprocal of cosine of pi over 3, so this would come out to 2, plus tangent of pi over 3 is rad 3. Secant of 0 is 1, it's the reciprocal of cosine of 0, which is 1. And tangent of 0 is 0. So indeed, ln of 1 is, of course, 0. So we have ln of 2 plus rad 3, which that's a positive number, so we don't even need the absolute value. So ln of 2 plus rad 3 is the arc length that we seek. It's the exact length of the curve. All right, so here again, we will use the arc length formula. And we can see that we have x as a function of y, and our bounds are also y values, say 0 to 2. So we're definitely integrating dy, which means that inside the integral we need a dx over dy. So in other words, we need the derivative of x with respect to y. Okay, so the derivative of x with respect to y is, well, derivative of 1 is 0. So this is just going to be e to the negative y. So our setup is the integral from 0 to 2 of 1 plus e to the negative y squared dy, which is the integral from 0 to 2 of 1 plus e to the negative 2y dy. Okay, so the next question is, how do we actually approach this integral? Well, wouldn't it be nice if this were 1 plus some quantity squared? Because then we would know that we could do a tangent substitution from that point. So, great, let's engineer things so that we have the radical 1 plus u squared. That means that we want u squared to be e to the negative 2y. In other words, we want u to be the square root of e to the negative 2y, which is e to the negative y. So that should be our substitution. Okay, well, let's do the substitution formally. So we'll let u equal e to the negative y, and therefore du is negative e to the negative y dy. So our integral becomes the integral of 1 plus e to the negative 2y. Well, we know that's u squared. And then our dy is, of course, du divided by negative e to the negative y, which could be written as du over negative u. The bounds of our integral we need to update. So when y is equal to 0, u is equal to e to the 0, so that's 1. And when y is equal to 2, u is equal to e to the negative 2. So this integral becomes negative 1 to e to the negative 2, rad 1 plus u squared all over u du. And we've engineered things so that we can do a tangent substitution. Let's do one more quick simplification before we do that. Notice that e to the negative 2 is a smaller quantity than 1. So we typically like to have the smaller number as the lower bound of the integral and the larger number as the upper bound of the integral. And the integral happens to be negative, so we can kind of kill two birds with one stone here by throwing away the negative and inverting the order of integration. We're using the property that the integral from a to b of f of x dx is equal to negative the integral from b to a of f of x dx. All right, let's do our tangent substitution. So we're going to let u equal tangent of theta. So du is secant squared theta d theta. Okay, well, what does this do to our integral? Well, worry about the bounds in just a minute. We have 1 plus u squared, which is 1 plus tangent squared of theta, over u, which is tangent of theta, and du is secant squared theta d theta. When u is equal to e to the negative 2, theta must be the inverse tangent of e to the negative 2, right? Theta is inverse tangent of u. So our lower bound is now inverse tangent of e to the negative 2. Not the greatest number in the universe, but it's fine. The upper bound will be theta equals inverse tangent of 1. Well, that's pi over 4. Okay, we know that this entire radical expression reduces to the radical of secant squared, which then just becomes secant. So when multiplied by the secant squared, we have secant cubed. So this is the integral of secant cubed theta divided by tangent of theta d theta. All right, so how do we integrate this one? Well, we've got a bunch of secants and tangents, so your instinct might be, hey, let's try and reserve something. Our options are reserve secant squared, but that would only leave a single secant, which is very difficult to turn into tangents. So the other option would be to reserve a secant tangent, anticipating letting u equal secant. However, we do not have a tangent in the numerator to do that. Now, you could manufacture one by writing, say, tangent of theta over tangent of theta. However, it's going to turn out that that's not a very nice integral either. So what we're going to do is what we did when we encountered secant cubed just by itself in an earlier lecture, and that was simply use integration by parts. So we have a secant squared as a factor of our integral, which means we can easily integrate that to become tangent. I think we should do that. However, I definitely think we should work out this integration by parts as side work. Now, we're not breaking the rules, we're using the letter u here because we're embedded in side work. So this is just completely separate work here. All right, so what we want is our dv to be secant squared d theta, because we know that's going to integrate nicely to tangent. So u is going to be everything else. So that would be a secant divided by tangent. Okay, well, isn't that just a cosecant? Oh, the answer is yes, it is. So our du is the derivative of cosecant, which is negative cosecant cotangent d theta. So that means that our integral, being ultraviolet voodoo, is cosecant of theta times tangent of theta minus, well, that'll be a plus because of the negative there, cosecant of theta cotangent of theta times tangent of theta d theta. Okay, well, cotangent times tangent, of course, is 1, so this is just the integral of cosecant And cosecant times tangent is actually just secant. So what is the antiderivative of cosecant of theta? That's negative ln of absolute value of cosecant theta plus cotangent theta plus a constant. So this is the end of the side work. So now we can return to the main thread and we'll use the side work here. So this is simply secant of theta minus ln of absolute cosecant theta plus cotangent theta from inverse tangent of e to the negative 2 up to pi over 4. Super fun. Let's plug those in and go home. So we have secant of pi over 4 minus ln of cosecant of pi over 4 plus cotangent of pi over 4. And we are subtracting everything with inverse tangent of e to the negative 2 plugged in. But rather than write out secant of inverse tangent of e to the negative 2, why don't we just draw a triangle? So let's defer this one more round, and we'll just leave it as secant of theta minus ln of cosecant theta plus cotangent theta. Where we know we're going to plug that in. So we know tangent of theta is e to the negative 2. So we can label these sides of this triangle, and we'll get 1 plus e to the negative 4 under a radical for our hypotenuse. And now we can read off the triangle, sine, cosine, tangent, whatever. So the next stage of our answer is secant of pi over 4, which is rad 2, minus ln of cosecant of pi over 4, which is also rad 2, plus cotangent of pi over 4, which is 1. Secant of theta, which is from our triangle 1 plus e to the negative 4, minus ln of absolute value of cosecant of theta, which is that thing, plus cotangent of theta, which is that thing. Okay, so what is this thing? This is rad 2 minus ln of 1 plus rad 2 minus, distributing this negative, we get square root of 1 plus e to the negative 4. This becomes a plus ln of 1 plus e to the negative 4, and then plus 1, and that's all over e to the negative 2. It's a naturally positive quantity. We can split that natural log up using the laws of logarithms, and it's definitely going to be worth doing that. Because we'll get plus ln of that numerator, and then minus ln of e to the negative 2. But this actually evaluates simply to negative 2. So negative of negative 2 is plus 2. And that is the final answer.